Hello and welcome to Calculus Lesson 145. We are almost there. You're almost there. Finish strong. Today we're going to talk about convergence of power series. What is a power series? Well, a power series is one that contains an x to the n, x to some power. Okay, usually there's some other stuff involved in our series, but it's multiplied by x to the n. Now the question we are asking is, will this converge or always, or more than likely, for what x's will this converge? Okay. Obviously, if x is a whole number, like if we have the sum of 3 to the n, this is not going to converge ever, right? But if you put x here, then you could go, well, maybe, right? If this is a fraction, then like 1/2, a fraction whose absolute value is less than 1, then this would converge. If this is a negative number, it could potentially converge. And so we have a little bit of work to do today. So here's the idea. A power series will converge, or if a power series converges, for an x, let's call it equal to c. So we have this series. We're going to say this converges for an x. There we go. Sorry, fixing the lighting there. For an x value equal to c, whatever c is. Then it converges absolutely when absolute value of x is less than the absolute value of c. So let's say we have a series that converges for x equals 3. Then we can say that it converges absolutely for any values between -3 and 3. So that's one thing. Obviously that makes sense because we should be able to do a basic comparison test and say that that new series is a little bit smaller. Now, next we have the following. If a power series diverges for a number, for let's say x equals d, I think this was c, then our series diverges for all x's whose absolute value is greater than that absolute value of d. Diverges. Also by basic comparison test. So if I say this x to the n diverges when x equals 1 or is greater than 1, then if I plug in 2, it's greater than 1, so that will also diverge. So that's all basic comparison testy things. Now let's talk about what's going to happen. We really only have 3 cases with a power series for these x values. The first case is that we find out that our power series only converges when x equals 0. Okay? So obviously when you multiply something by 0, that will always equal 0, so that's going to converge to 0. And so the worst case scenario is x equals 0 is when it converges. That's not bad. Next, the series converges absolutely for all x. So our second possible option is that we converge absolutely for all x. Okay? Maybe the an contributes something where x to the n is inconsequential. For example, if you had x to the n over e to the n, nope, that's not going to work. All right, well, we'll do an example in a second. Man, couldn't pull an example out of my head on that one. That's too bad. Well, I guess if you had x to the n over x plus 1, that series would converge absolutely because it's a geometric series where it's a fraction no matter what. And so whatever x is, the bottom is going to be a little bit smaller. We'll go with that. That may not be a perfect example. And then finally, and this is the most complicated one, so it either only converges when x equals 0, which means it basically diverges all the time. It converges absolutely for all x, so we have this convergence going on. Doesn't matter what we plug in, it will converge. And then finally, there is a positive number. Now I'm going to use a special math term. This means is an element of, but if we go backwards, whoa, that looks gross. This means there exists. So there exists a number x equals r, where r is a positive number, such that, I'm not even using the right, it should be a positive e. There. Why don't I just write it out? Well, let's make everyone's life easier. We'll write out the whole thing. Let's go into all crazy mathy on you guys. So there exists a positive number r such that the series converges absolutely when x, or the absolute value of x, is less than r, and diverges when the absolute value of x is greater than r. So those are the three cases we're looking for in our power series. So let's try a couple and we'll see if it works. Now the idea is that if you are falling into this third category here, you're going to have to find that r. So you're going to give the interval of convergence. That's basically saying it's going to converge around these numbers. So our first question is find the interval of convergence of the power series x to the n over n factorial. Okay, all right, here we go. So the easiest way to do these, and the most common, is either to do the ratio test or the root test. I'm going to do the ratio test here to see for what values of x this will converge. Remember, we do all of these tests with the limit as n approaches infinity, not the limit as x approaches infinity. X is a finite number that we'll have to plug in at some point. We're trying to figure out what values of x make this work. So what would the ratio test do? Well, it would make it x to the n plus 1 over n plus 1 factorial divided by x to the n over n factorial. Okay? This as n approaches infinity. Note that our x, there we go. Okay, x to the n plus 1 is simply x to the n times x, and that will cancel with my x to the n, so I'm left with x on top. N plus 1 factorial divided by n is n plus 1. So this approaches 0, and so based on our ratio test, we have that this converges. So no matter what value of x I plug in, this will always converge. So we have that second case where it converges absolutely for all x. So the interval of convergence is negative infinity to infinity. I can plug in any number to this and it will converge. Now, what is this series? Well, this is simply e to the x. It's the Maclaurin polynomial for e to the x. So we would hope that it would converge to a finite number. Otherwise, we have been lied to by our calculators and math teacher that e to the x is a number. Okay, let's try a different one now. We're going to find the interval of convergence of this one. We have n factorial times x to the n. This one's a little bit sneakier. So let's apply the ratio test again. We have n plus 1 factorial, which is just n plus 1 times n factorial. X to the n is, or x to the n plus 1 is x to the n times x divided by n factorial x to the n. So those cancel, and I'm left with the limit as n approaches infinity of n plus 1 times x. Now, for what values will this equal 0? Well, that is only when x equals 0. So we fall into this first case. It only converges when x equals 0. If x is any other number, the n plus 1, as n approaches infinity, will take over, and we will have no convergence. Remember that we struggled a little bit with infinity times 0. In this case, we want to remember that we're adding an infinite series of 0. So it's, when I plug in 1, I have 1 times 0. When I'm plugging in 2, I have 2 times 0. When I'm plugging in 3, I have 3 times 0, 4 times 0, 5 times 0. And so the answer is 0. Okay? A final example, find the interval of convergence of this guy. N equals 1 to infinity of negative 1 to the n plus 1, x to the n over n. Okay, so what are we going to do? Ratio test. Am I sure that this is the... Yeah, okay. So what do we do here? Well, first of all, I'm going to take the absolute value, so that gets rid of my negative 1 to the n plus 1. I want to figure out absolute convergence here. So take the absolute value. That's easy. So now I have x to the n plus 1 over n plus 1 divided by x to the n over n. Okay. So what am I going to do here? Am I on the right track? I am. This equals, well, if I take out the x to the n's, I have the limit as n approaches infinity of x over, or x times n over n plus 1. Now, I want this to equal 0. How do I get this to equal 0? A little bit tricky here. So, our x value is not a factor of the limit. So I can actually pull it out. This guy equals 1. So this simply equals x. So remember, the ratio test, we don't need it to equal 0. We just need it to be less than 1. If this equals 1, then we don't know. But if it's less than 1, then we know that it converges. So what that means is that I need x to be, and remember we're taking the absolute value of this, so I'm actually going to take the absolute value of x and say that that must be less than 1, because our ratio test requires for convergence that this value, the result of this process, be less than 1. Okay, so what does that mean? Well, x has to be between -1 and 1. So that's that third case where there exists a positive number r, in this case it was 1, such that x, this series converges absolutely when absolute value of x is less than 1, but it will diverge when it is greater than 1. And that, my friends, is problem set 145.